we also need to consider a graphical representation of the photoelectric effect formula as shown here. So if I rearrange this to make E max or KE max the subject, that's equal to HF minus phi. Then if I compare that to the standard formula for the equation of a straight line, y equals mx plus c, what that means is I'm going to plot the kinetic energy, the KE max, on the y-axis. I'm going to plot on the x-axis the frequency, as shown here, and then the gradient would be equal to h. So if I worked out the gradient of this line, it would be equal to the Planck constant. The y-intercept is always going to be negative, and the y-intercept will be the work function. This is a very typical exam question. You might be presented with a question like this, and you have to either calculate a value for the gradient, which should be equal to the Planck constant. They might ask you to read off the values. So the y-intercept would be equal to the work function, and we can ignore the minus. The x-intercept is the threshold frequency. Now if we apply this to what we've just been considering, the frequency can be any value that we apply. That's the frequency of the external light. If that is less than the threshold frequency, then the kinetic energy max is 0 and the electrons are not released from the metal. At the threshold frequency, they are released with 0 kinetic energy, and as I increase the frequency, the KE max will increase, which is what we saw in the simulation earlier on in the video. We could also compare two metals, so I might have metal A and metal B. Metal B has got the largest work function because it's got the largest value, the magnitude of the y-intercept. It also has a larger threshold frequency. However, we can see that these two lines are parallel. They both have the same gradient. The gradient is always the Planck constant. This is the final thing we need to consider. What is the energy of the photoelectrons, the electrons released by this effect? So we looked at the photocell circuit earlier on in the video. And when we did that, we had 0 voltage applied. What we can do with this is actually apply a negative voltage between these plates. So the electrons are released from this plate here, and previously there was no voltage applied. If I apply this negative voltage, that is going to repel my negatively charged electrons. And if I keep increasing the size of that voltage, at some point these electrons will not be able to make it to the far electrode. So what we would find is, as we increase the negative voltage, the current is going to start decreasing from its maximum value until it becomes 0. So just as the point where it becomes 0, the voltage applied is called the stopping potential, because it's the potential difference which causes the current to stop, or the electrons to stop traveling all the way to the other side. At that point we record the voltage, and then we can just multiply that by the charge on one electron, and that will give me the work done in stopping the electron, which is equal to the kinetic energy. So a simple worked example, if I, for a particular photocell circuit, a particular light and a particular metal, if I increase the voltage till it becomes large enough to reduce the current to 0, and I record that value, it's minus 1.2 volts, I can calculate the maximum KE of the photoelectrons. And in this case, it's a nice simple calculation. The KE is equal to the work done, which is equal to Q times V, the charge on one electron multiplied by 1.2, and we can calculate the maximum KE of those photoelectrons.